Hi, welcome to OpenLC Solutions. I'm continuing the series on 2014 ordinary level paper, and we're currently working on question 2, which is all about complex numbers. The very first part of this question gives you some complex numbers z1 and z2, and you're asked to find z1 minus z2. So it's just a purely arithmetic thing where you say z1 is 5 minus I because that's what you're given. And then you subtract 4 plus 3i. I'm going to put that in a bracket just to make sure that I get my signs right. So let me distribute that. That's going to be a minus 4, and then the minus will come in to the 3i as well. And so I end up with 1 and a minus 4i. We are then asked to verify that the modulus of this 1 minus 4i that we just worked out is the same as the modulus as if we reverse the order of that arithmetic. Now, given that we have z1 minus z2 from the first part, I'm going to work on z2 minus z1 first. So z2 minus z1 is going to be 4 plus 3i from z2 minus z1 is going to be 5 minus I, just putting that in brackets to make sure I get my signs right. So 4 plus 3i, it's going to be a minus 5 and a plus I, and so you end up with minus 1 and plus 4i. And now we have to work on the modulus. So let's say the modulus of z1 minus z2 is given by square root of the real part squared plus the imaginary part squared. So the real part is a 1, and you square that, and the imaginary part is a minus 4, so you square that as well, as you end up with 1 plus 16 in there, which is root 17. And if you want, you can work out all the decimals of that, but there's not really any reason to do that, and you'll see why in a moment when I work out z2 minus z1, or the modulus of that. So again, I'm looking for the real part, which is a minus 1, and that gets squared, and then the imaginary part is a 4, and that gets squared as well, so I get a 1 plus a 16, which is a root 17. And so both of these turn out to be root 17, so I can say that z1 minus z2 in a modulus is equal to the modulus of z2 minus z1, because they both turn out to be root 17. The third part asks us to give a reason why the modulus of z minus w is equal to the modulus of w minus z. Give a reason why that's always true for any two complex numbers z and w. There are a few valid answers to that, but the easiest one is probably just to say that z minus w is equal to minus w minus z, and you can see that that works out because the minus and the w will combine to be a minus w, and then the minus and minus z will become a plus z. And so really the only difference between these is that the signs of each of them are going to be different, and you can see from the previous part that z1 minus z2 is 1 minus 4i, z2 minus z1 is minus 1 plus 4i. So the real part and the imaginary part are kind of the same. They're just opposite sign, whereas the real part was a plus 1 originally, and then it was a minus 1 for the second question. The imaginary part was a minus 4 for z1 minus z2, and it turned out to be a plus 4 for z2 minus z1. So what we usually say is the modulus, or the absolute value, is another way of saying this, the absolute value is going to end up being the same because the numbers are the same, and when you're taking absolute values or modulus, the sign doesn't really come into it because it just means you sort of make it positive. And so you end up with this being true as well, where you can take the modulus of those. So and the idea, I suppose, is that the modulus cancels out this minus sign here, and so you just end up with this being true. And we should probably put some implies arrows on here. Another way of explaining this is, say you've got your Argand diagram, your z minus w, let's say that ends up being here. Your w minus z is going to end up being the image of that through a central symmetry, I suppose you could call it, the central symmetry being through the origin. And so when you're talking about modulus, you mean distance from the origin, essentially, the length of the complex number is another way of saying it. And so the distance to this one, z minus w, for instance, it has to be the same as the distance to w minus z, because it's an image in central symmetry through the origin. It just sort of has to work out that way. And you can explain it in so many words as well. You could probably just leave it as w minus z is the image of z minus w under central symmetry in the origin, and so the length of these two complex numbers has to be the same. The last part of this question asks us to find a complex number z3 such that z1 is equal to z2 divided by z3. And we have to give our answer in a particular form, but we can deal with that a bit later when the time comes. Now this is a weird way of phrasing it, I suppose. We can actually just rearrange this because it's really difficult to work it out as it is. But you can do either cross multiplication is probably something that you will have looked at, or you could just work it out algebraically that this is also true automatically. And so to work out what z3 is, you just do z2 divided by z1. To work out z3 then, we do z2 divided by z1, and now z2 was 4 plus 3i, z1 was 5 minus I, and this would be fine if it weren't for this little extra bit in the question that says we have to give our answer in this particular form. So we have to do a little bit of extra work on this, and the only thing really that we can do with this is a particular technique that you've probably looked at, which is multiplying top and bottom by the conjugate of the denominator. That is, taking 5 minus I, the denominator, changing it to its conjugate, which means changing the sign of the imaginary part, and you multiply that by that on the top and bottom. So we end up with a 5, and this time it's going to be a plus I, because the conjugate means you take the opposite sign of the imaginary part, and you do the same thing on the bottom, multiply by 5 plus I. And the only reason we're allowed to do this is because we're multiplying on the top and the bottom by the same thing. And if you want, you could like evaluate this new fraction that we have here. That's just a 1. So you're multiplying a number by 1, which means you're not changing its value, but we're doing it in a very clever way, which means that we can change how the number looks in the end, and it'll end up in this format that the question is asking for. Let me just get rid of this, we don't really need it. So we have to do a lot of algebraic multiplication here. So let's see, it's going to be a 4 by 5 plus I, plus 3i by 5 plus I. And we end up with a 5 by 5 plus I and a minus I by 5 plus I. This is just standard algebraic distribution, so hopefully you're familiar with that already. And we end up with a 20 plus 4i, and then a 15i plus 3i squared. 25 plus 5i minus 5i minus I squared. And this is the key thing, this is the reason that we do this, is that we end up with a plus 5i and a minus 5i. And so those two, when you add them together, you'll get a 0. It's also known as they'll cancel each other out. And so we need to evaluate this a little bit further. So we're going to have a 20. We're told at the very beginning of the question, that's something that you hopefully know as well, that I squared is minus 1. And so you've got 3 times I squared, which means 3 by minus 1, which is just a minus 3. And so we end up with a 17, because 20 minus 3. Then plus 4 plus 15 is going to be a 19i. And then on the bottom we've got a 25 and a minus I squared. Again, I squared being minus 1, which means this is minus times minus 1. We're essentially adding on a 1. So we end up with a 26 there. And it's still not quite in the right form, but now that we only have one number on the bottom, we can actually just do a division operation here. So we end up with 17 over 26 plus 19 over 26 times I. And that should just be the answer, essentially. And so now it's in that special form that we want. We have an A, which is 17 over 26, and we have a B, which is 19 over 26, and that gets multiplied by I. So it's in this format that we're given at the very beginning of the question. So that's it for this question. Thank you very much for watching, and hopefully I'll see you again in question 3.